All right, this is the gravimetric analysis practice quiz, and we're going to construct an answer key video. Number 1 states, a 10.00 gram sample of limestone was dissolved in hydrochloric acid, and all the calcium present was converted to calcium 2+. Excess ammonium oxalate solution was added to the solution to precipitate all the calcium ions out as calcium oxalate. The precipitate was filtered, dried, weighed into a constant mass of 12.93 grams. Determine the percentage by mass of calcium in the limestone sample. So the first thing you want to do with these types of problems is always try to figure out what the precipitate is. So in this case, they named the precipitate as calcium oxalate. So the mass of calcium oxalate is 12.93. Here's the formula of calcium oxalate. So that's where we're going to start. So we have 12.93 grams of calcium oxalate. Now remember, there's a couple different ways you could do this. You could do this by a percent by mass and say there's 40.08 grams of calcium for every 128.10 grams of calcium oxalate. That works. We can use stoichiometry. First, change this from grams to moles. And then pull the calcium out of there. Remembering that ions have the same mass as atoms because of the fact that ions are formed simply by losing or gaining electrons. So you can see that either way you do this, it's essentially the same thing. So if I do it with stoich like this, or if I do it with percent by mass like this, I'm going to get the same answer. And the answer is, so in your calculator, you're going to multiply across the top and divide by the bottom. And in this case, it's 12.93 times 40.08 divided by 128.1. Either way you do it, you should get the same answer of 4.04 grams of calcium ions. It says determine the percent by mass of calcium in the limestone sample. Well, we've got the mass of calcium, we've got the mass of the limestone sample. So it's 4.04 grams of calcium over 10.00 grams sample. Turn it into a percentage by multiplying by 100. And that gives me 40.46% calcium in the limestone sample. That's the answer to number 1. Move on to number 2. A 7.50 gram sample of an alloy containing only tin and lead was dissolved in nitric acid. So this is actually an alloy is a mixture. It's kind of a solution of metals. So we cannot get them apart without doing something like this. Chromic acid was added to the solution, which precipitated 4.35 grams of lead chromate. Assuming all the lead was precipitated, what is the percentage of tin in the sample? So what we did was we had a solution of tin and lead together. We dissolved it. The tin and lead ions were floating around together. We could not separate them unless we did selective precipitation by gravimetric analysis. So I precipitated out the lead, leaving the tin in the solution. So we're going to start with the precipitate here, which is 4.35 grams of lead chromate. I'm going to do it again both ways for you. It doesn't matter which way you choose to do stoichiometry or percent by mass. The mass of lead in here is 207.2 grams. And then we're going to have to add up the complete mass of lead chromate. So the molar mass of lead 2 chromate is 323.1937 grams. I'm just going to use a lot of significant figures. This is the off the periodic table, the elements that you get to use for the AP exam. So whether you use stoichiometry or percent by mass, it doesn't matter. You're going to get the same answer. And in my calculator, I'll multiply across the top 4.35 times 207.2 and divide by the bottom. And I get an answer of 2.78 grams of lead. Now, this is lead, but they're asking us for tin. Well, the tin's still floating around solution. How do I get that? Well, we know that this contains only tin and lead. So if we take this sample, which is tin plus lead, and then we subtract off the lead, we will get what's left over, which will be just the tin, which is what we're looking for. And I get an answer of 4.7112 grams of tin. So if we want to know what percentage that is, we'll just take the part that's tin, which is 2.7112, over the whole sample, which is 7.50. Multiply it by 100. To get 62, how many sig figs? 3.8% tin. That's number 2. Okay, let's move on to number 3. And this is the one that you did the ed puzzle for to try to understand a little bit. Here's another one we would have done a lab for had we been in class, and that would be the formula of a hydrate. So let's draw a picture and see if that helps us out. A crucible is kind of like a weigh dish that you can use you heat it up and you can drive the water off the sample. So the empty crucible has a mass of 8.960 grams. So the crucible and the hydrate. So here's how I'm going to draw the hydrate. I'll represent the salt, one color. And then we're going to represent the water. That's trapped in between the molecules, like such. And this is just a picture. So this is 14.177 grams. So this is just the crucible. This is the crucible. And it says plus the hydrate, so that's plus the salt, plus the water that's trapped in the salt. And then after heating the crucible and the anhydrous salt, where the water has been driven off and is in the atmosphere now, is not being weighed, that has a mass of 11.929 grams. So this is just the crucible plus the salt. So you can see this one's the crucible, the salt, and the water. This is just the crucible and the salt. So if I want to know the mass of the water, I just take the crucible plus the salt plus the water and subtract off the crucible plus the salt. So 14.177 grams minus 11.929 grams will give me the mass of the water. So 2.248 grams of H2O. Now, if I want to know the mass of just the salt, I would need to take the crucible plus the salt and subtract off the crucibles. So that is 11.929 grams minus the crucible, which is 8.960 grams. If you have to draw yourself a picture every single time, go for it, because these are going to be the types of situations where you're going to have to subtract some things to get what you're looking for, sometimes in the lab situation. And this is 2.969 grams of the salt, which is magnesium sulfate. So now we've got the different pieces. Well, if we want to compare these, we're going to have to change them to moles. So in order to change grams to moles, you divide by the molar mass. Let's figure out what magnesium sulfate is by looking at the periodic table of the elements and adding up the individual elements involved in there. And the molar mass for magnesium sulfate is 120.38. So this gives me 0.1248. We're going to try to carry around a few extra sig figs if we can. And this is 0.02467 moles. Now remember, in order to compare things in chemistry class, we have to divide. So I'm going to decide that this is the smaller number. So we're going to divide both of these numbers by this number. This will give me a 1 for magnesium. And let's see, 0.02467 12478 divided by 0.02467. And that gives me a ratio of 5 to 1. These are the ones that are not going to be exactly on the dot. And the reason for that is this all comes from experimental data. That means that the formula for my hydrate is MgSO4. This little dot means that it is a hydrate, so those are trapped in. And then I have 5 water molecules for every 1 magnesium sulfate. This is my answer. This is the chemical formula for my hydrate. Okay, we're going to do the last one, number 4, together. What mass of silver bromide is produced when 350 milliliters of 0.850 molar silver nitrate is added to 128 milliliters of 1.25 molar sodium bromide? So let's try to understand what's going on here first. So I have a beaker that has 350 milliliters. And I'm going to add it to a beaker that has 128 milliliters. And when I add them together, my volume is additive. So 350 plus 128 equals 478 milliliters. When that happens, I'm going to have some precipitate form on the bottom. That's going to be silver bromide. So let's do the chemical reaction here. Silver nitrate plus sodium bromide gives me solid silver bromide. Nitrate and sodium are spectator ions, so really what we have going on here is silver plus 1 ions finding bromide minus 1 ions. And forming silver bromide. This is my net ionic equation, ignoring the spectator ions. So first, let's write what's going on here. So underneath silver nitrate, I'm going to write 350 milliliters of 0.850 molar. Under sodium bromide, I'm going to add 128 milliliters of 1. Molar, like such. I'm going to do a BCA chart, so I want to get moles. So before anything happens in these beakers here, I can take the moles per liter and multiply them by the liters to get the moles. So remember, big M is moles per liter. So in order to get the number of moles, you'd want to multiply the molarity times the liters. So in this case, it'd be 0.850 times 0.350 liters. So remember, you want to get good at looking at that and saying, oh, 350 milliliters, that's 0.350 liters. And that gives me 0.2975 moles of silver nitrate. But 1 mole of silver nitrate has 1 mole of silver. So this is 0.2975. Let's do the same thing for silver bromide. 0.128 times 1.25 gives me 0.160 moles of sodium bromide. There's 1 mole of bromide for every 1 mole of sodium bromide, so this comes down here like this. You can see that bromide is my limiting reactant. So I'm going to produce 0.1600 moles of silver bromide. So we'll just add the molar masses of silver plus the molar mass of bromine and multiply it by the number of moles, and I get an answer of 30.0, how many sig figs? 3. So it was 30.048, so it's going to be 30.0 grams of silver bromide. And that's the answer key for the gravimetric analysis quiz, which will be immediately a day or two after I get back.